Name is Özatay and I'm from Bilkent University, Ankara, Turkey. And this is my project presentation for the Foundations of Magnetic Resonance Imaging course. The main goal of my term project is to investigate the magnetization and simulate the differences of relaxation times of different body tissues. There are two relaxation processes, transverse relaxation and the longitudinal relaxation. Nuclei are composed of neutrons and protons, which yield them to have positive charges. Also, a nucleus with an odd mass number or odd atomic number has an angular momentum, which is the basic principle behind the nuclear spins. In magnetic resonance imaging of an anatomy, the main focus is the nuclei of H atoms, which exist in excessive amounts because of the water. When these nuclei interact with a static magnetic field or with a RF field, the MR signal can be acquired. When an external magnetic field B0 is applied, nuclear spins align in the same direction with this field and create a net magnetization vector. This vector grows exponentially with time and reaches an equilibrium value of m0, which is parallel to the initial magnetic field. Since m is a function of time and approaches to equilibrium in the presence of a magnetic field, it can be adjusted for imaging considerations by using magnetic fields or RF excitations. MT have two components. First one is the longitudinal component, which is oriented in the same axis with the static magnetic field and determines the time of M to reach M0. Second component is the transverse component, which is oriented in the orthogonal plane to the static magnetic field and determines the decay of the transverse component. The contrast between the different tissues of the resulting image is defined by T1 and T2 values of the respective tissues, which create the intensity difference. All the tissues have different T1 and T2 values. When the tissue gets excited repeatedly before it recovers from the longitudinal magnetization fully, T1 weighted contrast is obtained. Fat components of an anatomy has fast T1 values, which yields a bright image when T1 weighted image is considered, whereas water components has slower T1 values, which cause them to seem dark in the resulting image. Spin echoes are used to obtain T2 weighted images. In imaging a brain tissue, T2 value of cerebrospinal fluid is much longer than the white matter and gray matter. Therefore, imaging CSF is easier with T2 weighted contrast imaging. When the gray matter and the white matter decays completely, CSF has decayed only a few. Therefore, CSF has better contrast compared to white matter and gray matter in the resulting image. I have implemented the equations derived for these concepts and the values given in the table in MATLAB and completed my simulations. Namely, I have compared the CSF, gray matter, muscle, lung, white matter, kidney, liver, and fat tissues in order to observe the differences of the relaxation times of these tissues. This plot is for the longitudinal relaxation of different tissues. When we observe the results of the longitudinal relaxation, we see that the CSF has the fastest rise and reaches the highest possible signal amplitude before the other tissues, whereas fat tissue has the slowest rise compared to others. All the tissues grow exponentially as expected and reach a steady state value after a certain amount of time. This plot is for the transverse relaxation of different tissues. When we observe the results of the transverse magnetization, it can be observed that CSF has the slowest decay compared to others, whereas it had the fastest rise in the previous case. Liver tissue has the fastest decay in this case. They all start from the same point but decay differently according to their T2 values. Therefore, it can be concluded that all the tissues in an anatomy have different T1 and T2 values and they can be utilized to acquire images with different contrasts. This is one of the main principles behind the MR imaging which makes it important.